Lesson 9. Chemical quantities. Objectives. Understand the molecular and mass information given in a balanced equation. Learn to use a balanced equation to determine the relationship between moles of reactants and moles of products. Learn to relate masses of reactants and products in a chemical reaction. Understand what is meant by the term limiting reactant. Identify the limiting reactant in a reaction. Learn to use the limiting reactant to do stoichiometric calculations. Learn to calculate the actual yield as a percentage of the theoretical yield. Stoichiometry, limiting reactants, and percent yield. 1. Molecular and mass information in a balanced equation. A balanced chemical equation provides two essential types of information: molecular, molar relationships, mass relationships. Example:
2 mayúscula H subíndice 2 más mayúscula.
2 molecules of hydrogen plus 1 molecule of oxygen chill or produces 2 molecules of water.
This equation tells us molecular level 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. Mole level, most important for chemistry. 2 moles of H2 react with 1 mole of O2 to produce 2 moles of H2O.
Look, this is very, very important. As you can see here, the moles, 2 moles of hydrogen produces 2 moles of water, but 2 moles of hydrogen react with 1 mole of oxygen. This is very important. This is the information that you get from the from the equation. Sorry. Let's see mass level after using the molar masses. Well, if you know that 1 mole of dihydrogen is 202 and you have 2 moles, the mass of hydrogen is S1. If you have only 1 molecule of oxygen and you know that the molecule of oxygen is 32 because it's made of 2 oxygen, then the contribution of the mass of oxygen is 32. And if you have 2 molecules of water and every molecule of water is 1802, how you get that? Well, I will show you immediately. Look at this. In H2O, you say 2 atoms of hydrogen, and every atom of hydrogen is 1 grams per mole. So the multiplication is 2. And 1 of oxygen, and every oxygen weighs 16 grams. Every mole of oxygen weighs 16 grams. Then you say 16, and then you add, and then you can say that the water molecular mass is 18 grams per mole. Now, look at this. In this case, you have the mass of hydrogen, dihydrogen, the mass of dioxygen, and the mass of the water molecule. As the mass is conserved in a reaction, you can say that the contribution of hydrogen, of the 2 molecules of hydrogen, plus the contribution of one molecule of oxygen, this plus this, must be equal to the contribution of the two water molecules. As you can see, the equation is balanced. This is very, very important. The equation is balanced. So, if you add 4 times 32, you will see that it gives you 3604. Then, the mass of the reactants is equal to the mass of the products, so the mass is conserved. This is a very important concept, okay? Let's see. We are going to use this equation that is already balanced. And you know that 1 mole of dinitrogen is 2. This is the ratio, or reacts with 3 moles of dihydrogen. And that 1 mole of dinitrogen produces 2 moles of ammonia, or 3 moles of dihydrogen produces 2 moles of ammonia. These are the ratios, the mole ratios that you get from the chemical equation. Let's continue. Now look at here. How many moles of ammonia form from 2 moles of nitrogen? Then what is given? 2 moles of nitrogen. That's why I put this here first. And what you are asked for ammonia? Then you say, according with the chemical reaction, you can see that 1 mole of nitrogen, look at here, produces 2 moles of ammonia. And look at here. And I write this in this way because I have to cancel mole of nitrogen with mole of nitrogen to get what I am asked for. Then you multiply and divide and you get your answer in the given compound, in the compound that you are asked for. Then always you have to know what is given and what you need. What is needed? Needed moles of ammonia, given moles of dinitrogen. Okay, let's continue with the following concept. In this case, listen.
Relating masses of reactants and products. To convert mass, you must go through moles. General steps. Convert given mass to moles. Use the mole ratio from the balanced equation. Convert moles of product to mass. Example. How many grams of CO2 form when 10.0 g of C2H6 reacts completely? Balanced equation.
Okay, here you have the balanced equation. Then what do you have to do? You have to convert this mass into moles. How? Dividing by the molar mass. And then you get the moles of this compound. But is that what you need? No. They need the grams of CO2. Then you have to convert moles of this compound into moles of CO2. How can you do that? Well, if you have the moles of this compound And according with the equation, you know that 4 moles of CO2 are produced from 2 moles of this compound. Then using this conversion factor that you get from the equation, then you can get the moles of CO2. But the question was the moles of CO2 or the grams of CO2. Then in order to convert moles of CO2 into grams, I have to multiply by the molar mass, and then you get the grams of CO2. Well, in this, I want you to stop the video in order to see this conversion that goes from mass to mass. But as you could see, you have, for example, you have first to convert the mass of the given compound into moles, then observe the ratio of the compound, in this case, this moles of this compound in the chemical equation, moles of A. Suppose you have moles of A, then the ratio in the chemical equation tells you that you have 2 moles of A per 3 moles of B. What you doing? When you cancel this with this, you get the moles of B. And after that, you divide the moles, you multiply the moles of B by the molar mass, and you get the grams of B. That is what you are looking for. All right. Stop the video, watch the explanation once again until you learn it. Now, let's go to see what is the limiting reactant. Let's see.
Limiting reactant, meaning and importance. The limiting reactant is the reactant that is used up first, limits the amount of product formed, determines the theoretical yield. The other reactants are in excess. Analogy: if a sandwich needs 2 slices of bread and 1 slice of cheese, having 10 slices of cheese and only 4 slices of bread limits you to 2 sandwiches. 5. Identifying the limiting reactant. Method: calculate the amount of product formed from each reactant. The reactant that produces less product is the limiting reactant.
Example. You have this reaction. Aluminum reacts with chlorine to form aluminum chloride. But you have 5 moles of aluminum and 6 moles of chlorine. Then you want to see which one will be over first. The one that is over first is the one that will produce least product. Well, let's begin by one of the results, the moles of aluminum, 5. And according with the equation, you know that 2 moles of aluminum produces 2 moles of aluminum chloride. That's why I use this ratio. Of course, 5 moles of aluminum will produce 5 moles of aluminum chloride. In the same way, 6 moles of chlorine, knowing that 3 moles of chlorine produces 2 moles of aluminum chloride, 2 to 3, then you get 4 moles of aluminum chloride. Well, compare 5 moles here and 4 moles here. which one is the smallest? The smallest in this case is this. So this is what we call the theoretical yield. Theoretical yield. And the product, the reactant that is over first, the one that produces the least amount of product. You compare this and this is the smallest. Then this reactant is what we call limiting reactant. And here you have the concept of limiting reactant and theoretical yield. Stop the video and watch this again until you learn it. Write in your notebook and you will learn it faster. Let's continue then. Let's continue.
Stoichiometric calculations using the limiting reactant. Once the limiting reactant is identified, ignore the excess reactant. Use the limiting reactant to calculate product formed. This ensures the answer reflects real chemical constraints, not ideal assumptions. 7% yield, actual versus theoretical. Theoretical yield, maximum amount predicted by stoichiometry. Actual yield, amount actually obtained in the lab. Formula.
The formula is the percent yield is the actual yield, the one that you get in the lab, because sometimes as if you were if you were cooking, sometimes you mix the same amounts of things and the product is smallest or bigger. Then generally you get in chemistry, you generally get the actual yield is smallest than the theoretical yield. That is the one that you get by calculus. Then you divide actual yield by the theoretical yield and multiply by 100 and you get what we call percent yield. For example, here the theoretical yield is 25 and the actual yield, as you can see, is the smallest, is 21.5 grams. If you divide this by this and multiply by 100, you can say that the percent yield is 86%. Then the percent yield is usually less than 100 due to losses, side reactions, or incomplete reactions. Let's see some tricky evaluation or tricky questions.
Tricky evaluation style questions. Question 1. A balanced equation shows a 1-to-1 mole ratio. Does this mean equal masses react? Correct answer. Crossmark no why mole ratios do not imply mass ratios. Mass depends on molar mass. Question 2. A student calculates the product using the excess reactant and gets a higher yield. Is this valid? Correct answer. Crossmark no why. The excess reactant does not limit product formation. Question 3. If the percent yield is 120%, what is the most likely explanation? A reaction efficiency was excellent. B. Measurement or calculation error. C. The limiting reactant was misidentified. D. Product was wet or impure. Correct answers B and D. Question 4. If the limiting reactant doubles, what happens to the theoretical yield? Correct answer. Heavy checkmark. It doubles. Why? Product formation depends directly on the limiting reactant. Question 5. Can a reaction have no excess reactant? Correct answer. Heavy checkmark. Yes. Why? If reactants are present in exact stoichiometric proportions, all are consumed.
Okay. As you can see, this lecture is very, very important. I I want you to stop the lecture, stop the video, and watch it again until you get the main idea about stoichiometry calculation. See you in the next video.